Yes, sure.
Yes. So, Mr. Abdulaziz, please go on. And
Okay. Okay. Assalamu alaikum, everyone. My topic is about enhancing the reliability of mobile free space optical links using Walsh-Hadamard transform. In this presentation, I will start with introduction about the about the free space optical link and about the Walsh-Hadamard transform. Then I will discuss the key issue in the mobile FSO system. What is the component of the system and the failure modes? Also, what is the reliability model of the FSO system? And then a review of existing reliability strategies and what is my proposed reliability strategy and what is the adopted reliability metrics. And also, I will introduce the research methodology that I followed in this work. And then what is my proposed modulation and detection techniques to improve the reliability. And then I will go over the reliability assessment approach, and following that, the result, and finally, the key findings or a summary of the work. So what is the mobile free space optical communication link? Is a point-to-point communication system that uses laser beams instead of radio waves to connect two moving platforms. Mobile FSO enables very high-speed, secure communication between mobile platforms where radio frequency falls short. Figure 1 is an example of a use case of mobile FSO, a UAV to a UAV FSO link. It can be also between, for example, a satellite to a satellite, between a ship and airplane. So this is just an example. In figure 2 here, an example of FSO in military application. For example, here we can use the capability of the UAV to give a prediction, to give a forecast, or sorry, to give like an image about an obstacle or a fence that the military convoy cannot pass. So this is just a typical application of this technology. Another thing I want to introduce is what is the Walsh-Hadamard transform. It is a transform similar to the Fourier transform, but uses a rectangular square wave basis function called Walsh functions instead of sinusoidal functions that we already know in the Fourier transform, which is sine and cosine functions. For example, in figure 3, on the left, we have a Walsh function of order 5, and on the right, it's Walsh-Hadamard transform. This Walsh function is of order 5. The order here is equivalent to frequency, but it is the number of the zero crossing. So this is a way to distinguish between Walsh functions, is by the number of the zero crossing. The mobile FSO battle issue is the link reliability. Mobile FSO depends on the acquisition, tracking, and pointing system to keep the laser beam precisely aligned between moving terminals. Figure 4 illustrates an ATP system for mobile platforms. As you can see in the figure 4, the ATP system is typically electromechanical equipment or device that is very complex and expensive. Sustaining a reliable link is challenging due to the difficulty of maintaining precise beam alignment and overcoming air turbulence and varying atmospheric conditions, while either or both transmitter and receiver are in motion, as shown in figure 5. As you can see in figure 5, it is a UAV to ground station mobile link. And as you can see, the vibration and the atmospheric turbulence are a problem that can reduce the received optical power at the receiver. Reduced optical power leads to data loss and link outages. The high-level key components of mobile FSO system, as showing in the figure 6, starting from the transmitter, we have the format block, which prepares and structures data for the transmission. Then we have the modulation block, which maps the binary data bits into waveform patterns suitable for optical transmission. Then we have the optical front-end block, which converts the electrical signals into an optical beam signal using a laser and transmit optics. Then we have the ATP system at the transmitter, which align and continuously steers the beam toward the receiver despite the motion or vibration. Then at the receiver, moving to the receiver now, we have the ATB system also, but at the receiver, the ATB role is to maintain and align the receiver, ensuring the incoming beam stays properly centered. Then we have the optical front end of the receiver, which collects the incoming light and converts it into an electrical signal. And then we have the detection block, which extracts the transmitted information from the received optical signal. And finally, we have the format block, which restores the recovered data into a structured format. Notice that the format block, modulation block, and also the format block and the detection block at the receiver are implemented in software. They are a digital signal process and not a hardware device or equipment. For the failure modes in the FSO system, as shown in figure 7, we have the Poynting loss. In the Poynting loss, the beam deviates from the receiver due to the platform motion or vibration. We have the tracking failure, ATB loss. The ATB system cannot maintain a lock between the transmitter and the receiver, as shown in figure 7. Atmospheric turbulence, which is a random refractive index, causes beam wander and phase distortion. Weather attenuation, for example, fog, heavy rain, dust, snow, can also degrade the link performance. Beam blockage, temporary physical blockage by building or any physical object. Background light interference, for example, sunlight or artificial light. Optical power loss caused due to long path or divergence of the signal, can reduce received optical power below the detection threshold. Finally, we have also hardware degradation and failure. For example, the laser beam power instability over time, detector sensitivity drop, or miscalibration of the optics. The reliability model of the mobile FSO here the objective here is not to compute overall system reliability, but to identify system dependencies and the component most likely to cause a link or system failure. A mobile FSO system is a series system as shown in figure 8, and also particularly in figure 9, where we have the RBD block, the RBD diagram. As you can see here in the diagram, the optical, first of all, this diagram starts with the FT, which stands for format block at the transmitter, then MT for the modulation block at the transmitter, OT for the optical transmitter, optical front end at the transmitter, AT for the ATB system at the transmitter, and C for the channel, and also the same thing for the receiver. The optical channel highlighted with red color because it is the most critical failure point in the system, followed by the ATB system highlighted in the yellow color, based on the identified failure modes. Additionally, the optical channel and the ATB system pose the highest risk due to the atmospheric variability and the extreme beam Poynting precision requirement on the ATB system. We reviewed the existing reliability strategies, and we identified two common strategies that we found in the literature. The first strategy is the hybrid FSO-RF, and the other strategy is the multiple input, multiple output FSO system. In the hybrid FSO-RF, we use the RF as a backup or as a complementary link to maintain a connectivity. While in the MIMO FSO, we use multiple transmit and receive apertures to achieve spatial diversity. Table 1 provides a comparative summary of the two strategies. As you can see here in Table 1, in terms of the failure mode, the strategy A focus on the path blockage, focus on the fog and let's say on the weather conditions. In the MIMO FSO, we focus on the jitter and signal fading. The reliability goal in the strategy A is near 100% link availability, while in the MIMO FSO, the goal is to maximize the throughput and the link stability. In terms of complexity, in the hybrid system, we have two different links, but in the MIMO, we have multiple units of the same layer. In terms of the common cause of failure in the hybrid FSO, it is low because we are using RF link, which is unaffected by weather conditions or objects, or that the optical system is sensitive to, or affected by. Also, in terms of the MIMO, for the MIMO FSO, the common cause of failure is high because the fog cam blocks the optical link. The challenges for the hybrid FSO are typically in the handover latency to switch between the, you need to identify the conditions or the situation where you need to switch between the FSO to the RF link. In the MIMO FSO, the challenge is the channel correlation because you are using multiple channel in parallel. So there is a possibility of correlation between these channels. Application and strategy based for critical missions where we need to maintain link availability most of the time. For the MIMO FSO, the application is to in high capacity application, data application. In terms of security, the hybrid FSO is moderate because the RF is vulnerable to interception and jamming. For the MIMO, the security is high because there is low probability of interception. In terms of cost, the moderate it is moderate for strategy A because we have a dual RF FSO system and integration, and high because high in the MIMO FSO because we have multiple aligned optical units. Figure 10 here illustrates the underlying architectural solution of the two reliability strategies. As you can see in the hybrid FSO RF, the both system are totally the system are totally in parallel. There is no series component in the system. However, in the MIMO FSO, the only the parallel component are the channel, the optical channel, but the other component in the system are in series. A hybrid FSO RF strategy ensure connectivity during adverse weather, while MIMO FSO mitigate atmospheric turbulence and preventing error, which jitter. Our proposed reliability strategy goal is to ensure accurate data delivery and consistent link availability. The strategy is to reduce operational stress and precision requirement in the ATP system by designing FSO modulation and detection techniques based on the following: flexibility to changes in the channel state dynamics, for example, change in the link distance; resilience to channel impairments, for example, vibration, air turbulence, etc.; tolerance to synchronization or timing loss between receiver and transmitter. Figure 12 highlights the targeted blocks in the mobile FSO system. As you can see here, we focus in our strategy, we focus on the modulation block at the transmitter and the detection block at the receiver. Finally, the proposed strategy is not an alternative to existing strategies, but it is a simple, low-cost solution that can be a complementary or a standalone solution. Adapted reliability, we focused on the bit error rate and didn't consider other metrics such as MTBF or MTTF, outage probability, link availability, for the following reasons. Unlike static FSO, mobile FSO focuses on reliability in terms of performance rather than the classical hardware fault and failure, where success is maintaining acceptable communication quality, not a hardware survival. Bit error rate directly measures the end-to-end communication quality of the link, as it is inherently includes effects of the turbulence, noise, mobility-induced misalignment. Finally, BR is widely accepted metric for comparing and evaluating communication system under varying conditions used in the IEEE and ITU-T frameworks as a key performance and reliability metric. The bit error rate can be computed, or the formula for the BA is the number of the incorrect received bits to the total divided by the total number of transmitted bits. For the research methodology, we adopted the framework as shown in the figure 13. We started with this system definition. We defined the system environment and it defined what is the channel impairments, dominant channel impairments, and the mobility effects. Then we modeled in the phase 2, we modeled the system using standard models. Then we define the reliability metrics that we need to use in this work. Then moving to the phase 3, we design the modulation and detection technique and set optimization objective. Then in the phase 4, the evaluation, we perform the Monte Carlo simulation and benchmarked against a baseline modulation detection technique. Following that, we had to decide either if the reliability is improved or not. If the reliability improved, we need to, if not improved, we need to refine the design. Otherwise, the design is okay. Further details about the system model that we used is here in this equation, y equal RHX plus N. This is the big picture of the model of the mathematical model of the system, where y is the received electrical signal, r is the photodetector responsivity, h is the channel gain or the fading coefficient, and x is the transmitted optical signal, and n is the additive white Gaussian noise. For the channel coefficient, we focused on the three main effects, which is the path loss and the Bowenting error, and the jitter is one type of the Bowenting error, and the atmospheric turbulence. And as we said before, for the reliability metrics, we only considered the bit error rate. The optimization objectives, as we discussed before, we focus on the flexibility to the changes in the channel state dynamics, resilience to the channel impediments or noises, and tolerance to the time shift or the time loss between the transmitter and the receiver. In terms of for the evaluation, we performed a bit error rate sensitivity analysis under stochastic channel impediments and system parameter variations. Then we benchmark comparison against near idle on-off keying modulation with direct detection technique as a baseline to compare against. Here is the proposed binary Walsh keying modulation technique. Two Walsh functions are used as a signal patterns for transmission over optical channel. One Walsh function to represent the bit 1, and the other Walsh function to represent the bit 0. Figure 14 illustrates an example set of Walsh function. Here in figure 14, we see the first 8 Walsh functions. So we can select any two distinct Walsh function from these to transmit over the optical channel. For the detection technique, we proposed a Walsh-Hadamard transform based on the base detection. We apply the Walsh-Hadamard transform to the received signal at the receiver, and then we compare the coefficients corresponding to the selected Walsh pattern. The higher coefficient indicates whether a 1 or 0 was transmitted. However, Walsh-Hadamard transform is variant to the time shift, in other words, sensitive to the phase shift or time delay, which is a limitation as shown in figure 15. As you can see in figure 15, in the top we have a Walsh function that is not shifted or not experienced the time delay, and the following or the underneath figure is the coefficient or the fast Walsh-Hadamard transform coefficient of this signal. So here we don't see any issue. However, when this Walsh function experience a time shift or a circular shift by 50 sample, or even if it is one sample, if you take the Walsh-Hadamard transform of that signal, as you can see in the last figure, the coefficient will be mixed, and you cannot identify the transmitted signal. So to address this issue, we proposed another detection technique, and we called it Walsh Q-spectrum template matching detection. While the Walsh-Hadamard transform is inherently time shift variant, it exhibits a set of shift invariants known as the Q-spectrum. In this work, we exploit the underlying Q-spectrum properties with respect to the time shift, to design a detector that is robust to the time delay or synchronization loss. Figure 16 illustrates the proposed detection algorithm based on the Q-spectrum. As you can see in the figure 16, This algorithm starts with the received signal by applying the cyclic autocorrelation to the received signal. Following that, we apply the modified Walsh-Hadamard transform after the cyclic autocorrelation to obtain the Q spectrum. Then we compare we do a Q spectrum template matching by multiplying this the received Q spectrum for the received signal with a reference Q spectrum that is correspond to one the waveform 1 and the other one for the waveform that correspond to the bit 0. Based on this process, based on this likelihood probability, actually depends on the score of the multiplication. If it is the higher one is the, for example, it will be bit 1, otherwise it will be bit 0. However, it depends on the convection on which wave we have selected at the modulation block. For the reliability assessment approach, we have 3 system FSO system that we are considered. The first system is the near idle benchmark model based on on-off keying modulation with direct detection, and another FSO model based on the binary Walsh keying modulation with Walsh-Hadamard transform for detection. Also, the other one is the proposed modulation based on the binary Walsh keying modulation with Q spectrum template matching for detection. The reliability of the 3 mobile FSO system models was evaluated to enable a comparative assessment as shown in figure 17. We started first with the input generation. We defined the deterministic and stochastic parameters for the 3 mobile FSO system models, and we generate random bits of 1 and 0. Then in stage 2, we estimated the BER using Monte Carlo simulation for the 3 models under different channel realization. In the stage 3, we performed sensitivity analysis of the BER under varying stochastic channel impairments and system parameters to identify the condition that most strongly influence the system reliability. Finally, we perform analysis to compare the BER sensitivity curves of the 3 models to quantify the reliability improvements. In figure 18 illustrates the simulation procedure implemented in MATLAB using Monte Carlo method to estimate the BER. The algorithm, this is a pseudocode algorithm, start with defining system parameters, define random variables, then initiate the error counter. Then inside the loop, we generate random bits based on uniform probability because we don't want any bias. Then we map this bit to a signal. So this is a modulation, and then we apply the system model. We add the noise and another variables. Then we decide the received bit if it is 1 or 0. So here it is the detection. And then we compare the transmitted bit with the actual bit that is transmitted to calculate the bit error rate. Here is the result. Here is the result of the bit error rate with respect to the link distance. Figure 19 illustrates the bit error rate performance of the 3 techniques across varying link distance using the system parameters showing in the table 2. As you can see in the figure 19, beyond 5,000 meters, the bit error rate starts increasing. However, as you can see, the baseline modulation technique and detection technique outperform our proposed techniques. In terms of the optical bit error rates with respect to the optical transmit power, as shown in figure 20, we can see that also the OOK modulation technique with direct detection outperforms our proposed technique. However, in terms of the Poynting error, and particularly in terms of the jitter, as you can see in figure 21, our proposed techniques outperform the standard or the baseline modulation detection techniques. And this is the main contribution in this work because we are focused on the jitter and the atmospheric turbulence. This is another curve, sensitivity curve. This is the bit error rate with respect to the index of refractive structure parameter. This index is correlated, or sorry, this index is a quantitative measure of air turbulence. As this parameter value is increasing, the air turbulence is also increasing. As you can see, between 10 to the power minus 16 to approximately 10 to the power minus 14, the baseline modulation detection technique perform poorly in this region. It corresponds to moderate to strong turbulence, because it is very sensitive to the amplitude of the to the variance of the changes in the or it is very sensitive to the changes in the mean of the optical signal amplitude. Here we have the result of the bit error rate with respect to the atmospheric attenuation coefficient. As you can see in figure 23, uh, all techniques almost perform similarly in terms of the clear weather and in the and perform badly in terms of light fog and heavy fog. Finally, here we have the bit error performance with respect to the timing offset. Here we only consider the binary Walsh keying with Q spectrum template matching technique, because this is only the modulation technique and detection technique that is adaptive to the time shift. Other systems or other techniques need other system. They need, for example, phase lock loop to handle the time delay. But for this technique, it can handle the time delay. As you can see, if you shift the signal even up to, for example, if the signal is here, we use the signal of length of 1,000 sample. Even if you shift the signal by 500 sample, that means you lose 50% of the signal energy. The receiver can still detect the signal, the incoming signal. Finally, here we have the in table 8, we summarizes the bit error rate performance of the three modulation techniques, modulation detection technique under various system parameters and noise levels, with key criteria highlighted in the yellow. As you can see in table 8, if you see in the AOK/DTT outperform our proposed techniques in terms of link distance and optical transmit power. However, in terms of Poynting error, jitter, and atmospheric turbulence, timing offset, and adaptivity, our proposed technique outperformed the baseline or the benchmark technique. Finally, our proposed technique, modulation technique, are suitable for high mobility, high misalignment environments, as well as low-cost, short-range applications, by one, being simple and adaptive to the changes in the channel state dynamics. Two, partially shifting the burden of reliability from mechanical domain to the digital signaling domain. And three, being resilient to timing offsets between the transmitter and the receiver. Potential applications include UAV links, vehicle-to-vehicle communication, indoor optical wireless systems, mobile robotics, and short-range maritime links. Thank you for listening. If you have any question, I will be happy to answer your inquiries or questions.
Yeah, thank you so much. Excellent, Mr. Abdulaziz. I enjoy a lot actually. Both topic and your presentation was very, very perfect. I have
Thank you.
one question. Which software did you use for to simulate this algorithm?
MATLAB. Yes,
MATLAB.
MATLAB, as mentioned here.
Yeah.
Yes, yeah,
And
yeah,
based on
mentioned.
your literature review and search in other papers and to compare the research gaps, do you think is there any contribution for this proposed algorithm?
Yes. First of all, the main contribution or the novelty in this work is that nobody has used or modified the Walsh-Edman transform or optimized the Walsh-Edman transform for the use in to optimize the reliability, to increase the reliability of the mobile FSO system.
Mhm,
Usually, Walsh-Hadamard transform is used as a multi-carrier modulation technique. For
mhm,
example, in KIDMA system and OFT system, to allow multiple users to share or to transmit in the same channel. But this is traditionally in the RF domain, not in the optical domain.
mhm,
Also, nobody, no, we didn't, up until now, we didn't identify any paper or any document that has utilized the Q spectrum template matching technique for detection. Even though this technique was based on in paper in the 70s, where at that time Walsh-Hadamard transform was famous, maybe more than the Fourier transform, because at that time the computers where performance was very slow compared to the nowadays, because Walsh-Hadamard transform is way much efficient than Fourier transform. So we have the mathematical formulation for how to obtain the Q spectrum,
mhm.
but we adapted this, or we can say we use this technique in application that is nobody has used before.
Okay, so do you think can you draw a draft of paper and are you
Yes, yeah, and,
interested to submit
yeah,
this paper with
we
each other?
already in process. We already
Okay.
submitted and it is under review. It is
Oh, did
already
you
under review.
submit
And
the with
yes, just last week we it is under review, and maybe we need to do some modifications. So it will
okay.
be soon. Yeah, yeah.
Yeah, yeah,
Hopefully it
very
will
good.
be.
Very, very good.
Yes,
And please, actually, let me just share my screen. Please
yes.
stop your sharing.
Sorry.
This one, sharing. So, first of all, Mr. Mr. Umar Al-Harbi, you send your homework here. It is not correct. Please go to the content, and here you can upload your homework here. Five students already uploaded. So please upload all of your materials here. So PPT or and whatever you prepare, please upload here, and I can submit the overall feedback here. And regarding the uh, your assignment project, please upload your PPT and also PPT and Word file here and Mr. Abdulaziz, if it is possible,
Yeah,
um, make a zip file including the rest of the files you want to attach with this one, including the paper, everything you want, you know. And I already prepared this PowerPoint regarding your report, including the written report, you know, clarity of
just
argument. Yes.
just a quick question. For the presentation, I have the PowerPoint in the Keynote format. It is for Macintosh systems. Is it okay if we convert it to PDF type
Yeah,
format?
yeah, PDF type, and you can upload it here. Yes.
Okay, okay,
And then
perfect.
who already uploaded, I can have the list of students here, and I can just, for example, you can automatically, I can just select and all of the the marking can be added. So excellent means, for example, 100% of the marking, you know. But for example, if there is some comments, I can give you 12 out of 14, for example. You know, satisfactory is means 10.5 out of 14. But your marking can be between 7 up to 10.5 based on my comments. Did you understand me? So this is very easy. And finally, I can add some overall feedback. I can add some comments on your presentation and everything. So this way is very professional. It can help me a lot to give you my marking very fast, you know. Let me take off this one.
Also, just another question. So you need the presentation along with other files, including, for example, pictures,
Yes.
papers.
Yeah, yeah, yeah,
Okay.
yes, yes. But the presentation should be in separate
Right.
separate file because I can add some comments on the presentation.
Okay.
And also the assignments report also should be in separate file. Okay. So thanks a lot, Mr. Abdulaziz. Really, I enjoy a lot for your presentation. Who is the next presenter? So, Mr. Abdulaziz, I can upload this recorded video as a public, right?
Yes, yes.
Oh, okay, thank you. So, who is the next? We have a 15-minute, only 15-minute time. So, please tell me faster. And uh, if you are in middle of the presentation, we can go to the next link, okay? So, who is the next person? Mr. Muhammad Zamanan, Mr. Turki Al-Ghahtani, Mr. Muhammad Al-Ghamdi, Abdullah Al-Harbi, who can present right now? Please do it because during this period you can modify your presentation and upload again. It's okay. We don't have so much time. We only have 3 weeks uh, remain, and after that semester will be finished. Okay. So, Mr. Let me call you Mr. Abdullah Al Juhani. Please share your screen. Mr. Abdullah, are you hearing me?
Yes,
Yes, Mr.
yeah, I
Abdullah.
hear you.
Yes, salam alaikum.
But
Please.
I didn't prepare the presentation today. I was
Uh,
supposed to be next week because you told us in the group you have to finish the student that you picked first.
no, I mentioned that everybody should be ready, but the first 7 students should be almost 100% ready. So let
Oh,
me ask.
I,
Yeah, we don't have so much
that's
time.
why.
We only have 3 weeks, so everybody should ready the presentation. This is the last time I'm saying. Okay, Mr. Abdullah, please be ready for the next time,
I
next
thought
week.
gonna be in the next group, so that's why I didn't
No, no,
prepare
no, no.
today.
Please, everybody should be ready for presentation. Okay, Mr. Abdul Rahim, Mr. Abdul Rahim Dawi. Uh,
Yes, Dr. Musa, yes, I
yes,
hear you.
yeah. Please share your screen and start your presentation.
All right, Dr.
Thank
Musa.
you so much. So we only have 10 minutes. Uh, After 10 minutes, I will let you know. Please come to the other link, okay? Because automatically the session will be stopped. Okay, please. move on.
Yes, Dr. Musa, yes.
Yeah. Yes, please.
Yes, Bismillah ar-Rahman ar-Rahim. Today I'm going to talk, just a minute, Dr. Musa, just a minute, sorry. Yes, my presentation is about transformer reliability in power system. I will talk about introduction and then how market coupling works, benefit, and comparing. Yes, I will start with the introduction. This presentation proposes a new and practical probabilistic method for calculating reliability indices of substation which has a spare transformer of the same group. Based on Monte Carlo simulation, the proposed algorithm considers the chronological representation of failure occurrence by modeling emergency actions to ensure electricity supply to customers during the replacement of failed transformer. The research objectives, the first one is to have systems with a high availability combined with the lowest possible investments. The second research objective is to minimize failure risks of transformers, and then the third, reduce the number of spare transformers and improve system reliability. About the literature review and key findings, primary failure causes. Literature identifies winding isolation breakdown, moisture or thermal stress, and overloading as the leading causes of transformer failures. Critical components, bushings and windings are the most fragile components, with 44% of forced outage in large transformers. Aging and maintenance. Although designed for a 40 years life, many transformers fail much earlier, 10 to 15 years average, due to excessive stress, requiring a shift from time-based to condition-based maintenance. Algorithm flow chart. This is the algorithm. Start and then read system data and planning parameter, and then goes to the next step, which is in sim equals 1. I will read the steps. The first, read deterministic data from each substation, number of transformers, peak load, and load transfer. Read reliability data, number of spares, probability distribution of times to failure for each transformer and backup transformer installation. Specify economic data and system planning parameters, analysis period, load growth, rate transformation, park expansion plans, and spare stock expansion, new transformers prices, electricity price, and interruption cost of consumers. All these three steps actually happens here in the read system data and planning parameters. All these three steps. And after that, initial the analysis period, simulation counter nsim equals 1, which is this step. And then go until the period length is reached. For example, if we have to apply this analysis during 10 years. And in this step, the calculation of reliability NCDs are updated, which is this steps. If it is no, draw times to simulate system operation, and then we go back. But if yes, go to the sixth step, which is if convergence is reached, go to step 7. Otherwise, do NSIM and which is equal NSIM plus 1, which is this one, to create another analysis period and go back to step 5 again. And the step 7, calculate and store expected reliability and cost NCDs here, and then the system ends. About reliability NCDs, we have 4 NCDs. The first one is the unavailability, corresponds to the average number of hours in the analysis period during which the system is down, and this is the calculation, total time divided by NSM. The second indices, expected failure frequency, is the average number of failure observed in the analysis period, and this is the formula, total number of failure divided by NSIM. And the fourth NCDs is expected failure duration, and this average interruption duration of failure, the total downtime, the equation, divided by total number of failures. The fourth one is expected energy not supplied, EENS. This represents the average value of energy that the system fails to deliver in the period due to failure. The total energy not the equation, total energy not supplied divided by NSIM. Here is a numerical example. A substation has a stock with 7 transformers, spares, and expected frequency of 22.30 failure in the period, average 2.23 failure per year. And an average duration of 10.8 days are evaluated to achieve the required accuracy. NSIM equals 131.793, 10 years periods are sampled, where 8,760 is the number of hours in NIE. This table shows the reliability NCDs overall 10 years. F, which I says before, expected failure frequency, around that is 22.3, and the U, which I said before, unavailability, 5,777.91 hours per 10 years, and EANS, which is the expected energy not supplied, is 76,975.81 megawatt hour per year. These are the value NCDs for analysis period for year averages. Here is the table shows the unavailability of each year. The solid blue line, the blue line here, it's an average value over the period. The red dashed line, it's the performance indices, and it is better in the first year. This is due to the initial condition of the system, which is the 177 transformers in operation and all 7 spares available in stock. This is, for example, the case as we stated before. This diagram shows the stratification of system failure. This one shows 4 groups. The first group is the duration less than 4 hours after installing the transformer and using the spare parts. The second group between 4 hours and 3 days and the third group between 3 and 11 days, and you can see here a percentage of occurrence happens a lot. And the fourth group over for 11 days. The classes as defined according to the time required for load transfer. So we can transfer after the duration over 11 days. Here, the diagram shows the time of failure for new transformer. In order to assess the remaining life of a used transformer, the histogram should be conditioned to the age of equipment analysis period. And we can see here after 40 years to 60, the occurrence or the probability increases of failure.
So, Mr. Abdul Rahim, please
Yes.
go to the next link, okay? I will back to
Okay.
the next link. Thank you. Cheers. Sorry,
Okay.
everybody. Yeah, thank you.
No problem. Thank you.
Mr. Fahd, salam alaikum. Just give me a few minutes to have more people in the class.
Most welcome. عليكم السلام ورحمة الله. Okay, دكتور.
Yeah, thank you. Yeah. So, Mr. Abraham, please keep continue your presentation.
Yes, Dr. Nasser.
Yeah, thank you.
I stopped right in the recommendation here, recommendations for enhanced reliability. The first one is condition monitoring, real-time monitoring of winding temperature and bushing capacitance is crucial for early fault detection. And the second one is operational optimization. Adopting dynamic thermal modeling helps manage load without exceeding safe operating temperatures. The third one, protection improvements. Upgrading protection include advanced digital relays and transformer monitoring. This help prevent failure, particularly in aging assist. Future trends. About the future trends, we can use artificial intelligence, AI, using machine learning and intelligent diagnostics to predict failure by recognizing patterns in data. And the second one is the smart transformers, self-diagnosing intelligent transformer designed for smart grid integration. Conclusion, probabilistic method for evaluating the reliability NCDs for a group of similar distribution transformers with a given number of spare units. The Monte Carlo simulation, which are used in this presentation, made it possible to consider any probability distribution for the transformer failure times which represent exerts in a significant influence on reliability NCDs and operating cost. And these are the references which I used to make this project. Thank you very much. Do
Thank
you
you
have
so
any questions?
Yeah, thank you so much, Mr. Abdurrahim. Please upload everything in the Blackboard and I will review your report as well. Thank you. So,
Thank you very much, Dr.
thank you so much, Mr. Abdurrahim. So let me ask other students to share your screen. So, who is the next? Okay. So, Mr. Fahad, Mr. Faisal. Yeah, Mr. Faisal. Yes.
Yeah.
Salam alaikum. Yes. Please
Salam
share
alaikum.
your screen, Mr. Faisal. Yeah.
Dr. Musa, sorry,
Yes.
I
Yes.
need to upload the PowerPoint presentation plus the essay, which is the
Yeah.
PDF file of the project, right?
Yeah, PDF file of the project and the rest of things, including, for example, code, MATLAB code or simulation, whatever you have, you can make a zip code and upload again in the Blackboard.
Okay, okay,
Okay.
Doctor. I'll do it,
Thank you so
inshallah.
much. Thank
Thank
you. Yes. Mr. Faisal, let me write your full
Yes.
name. Yes. Uh,
Present something else.
entire system, entire screen, the last one, yes,
Yeah,
entire
enter
screen.
screen. Yeah.
Yes, select
Okay.
the entire screen again.
Okay.
The yes, this one, select this one, yes, yeah, and share. So what happened? So go to the your PowerPoint. No, go to the PowerPoint. Just minimize this one. No, it's okay. Let's cancel and
It's
minimize
okay
this
now.
one. Yes, yes, we have your screen. So minimize this Explorer and go to the open your screen, your PowerPoint.
Okay, just a second, please.
السلام عليكم دكتور موسى.
Salam alaikum. Yes.
دكتور about exam.
Yes. Could you please change your name? YK. I don't know what does that mean. Please.
I cannot every time make it I cannot والله دكتور. I
Okay. I
don't
don't
know
know.
why.
Okay. Your name is Yazid or I don't remember.
عبد الله
Abdullah. Yes. Yes. Abdullah.
عبد الله الشلبي.
Okay. Yeah.
دكتور about exam.
Yes.
It is online, right?
No. Exam will be in person. We don't have an online
It
Could
exam.
you
is
see it now?
Yes. We have your screen.
دكتور because it is impossible.
Sorry?
We cannot coming to Jeddah. We cannot coming to Jeddah
Why?
to Hajj. Hardly.
What
Because
happened?
Hajj it is every time there is.
So I don't know about that. So Mr. Abdulaziz, what's happened? Students cannot come to the Jeddah. I didn't know that because of course this is a in-person final exam, so it cannot be online. Let me see the presentation and please drop a message in WhatsApp group, okay? All right, Mr. Abdullah.
Could you see my presentation now? Yeah.
Yes, Mr. Faisal. Yes.
It's okay now.
Yes.
Assalamu alaikum wa rahmatullahi wa barakatuh. Today I'll present my presentation for my project, a wireless health monitoring system in response to COVID-19 situation. This project is we can use it like for COVID-19 or any isolation situation. It's not like just for COVID-19, but the COVID-19 is like, for example. So can you hear me now?
Yes, yes.
The aim of my project, the aim is to develop PHMS, which is Patient Health Monitoring System, in response to COVID-19, that will collect and organize the data on heart rate and oxygen, and also saturation level and the temperature of the room, and also for the air quality of the room, and also for fail detection when the patient in the bed, when he fell out, there is alarm from the patient without getting close to the patient. So the doctor now he can like control the everything in the room from far away. The objectives of this project, the first one is heart rate is one of the most vital parameters regarding human health. The heart rate will be measured by a sensor, and the patient's well-being will be notified to the doctor. If like there is any problem in the heart rate, there is like message, it comes to the doctor, and he will come straight away. The second objective is the blood oxygen has to be expected under 95. When the blood oxygen like under 95, there is alarm, it comes to the doctor. The blood oxygen level will be measured to check the patient health. A sensor will be used to measure the blood oxygen level just by putting the finger on the sensor. Just the patient, he put like his finger, like when he got like under 95, there is alarm or message come to the doctor. The third one is the heart rate will be monitoring using the system, and the doctor will receive an alert from the application at the same time. The surrounding temperature, that means the surrounding temperature, there is like temperature for the room, be controlled as per as the patient's health. Be using IoT application. Number 4, the patient always needs like a good environment to get back to normal life. There is a need for a temperature, humidity, and the air quality monitoring system to check the values around the patient. The temperature and the humidity and the surrounding air quality will be measured, and data will be transmitted direct to the Internet of Things application. So we can use there is applications is named Blink. That's we use it in my project. Number 5, an elderly patient, there is a risk of fails. The patient has less strength to walk during the days of recovery due to the health to their health condition. The core material, according to WHO report, ventilator disease causes 17.9 million deaths every year. It's imperative that improved health care systems be developed in order to detect chronic problems early. Its use of effective therapies in urgent instance. The IoT-based health monitoring system have a number of benefits on normal health care system. Medical gets that the patient can keep tabs on their health have shown out recently. So and this application and for this project, so we use it like in the hospital. If the hospital there is too many patients, and we have like risk doctors, so we use this IoT application to cover all the patients. That's the design of methodology. As you can see now here, here. That's the diagram. SpO2 for the blood. It comes to the controller, then send to Blink. Blink, that's the application. Then like send like email alert or message to the doctor. So that's the procedure of the project here. That's the hardware components. So we can use MAX 30100. That's a component, and also we can use MQ135 and MBU 6050 and the all LED display, so that we can read everything.
Mr.
And
Faisal,
also new,
Mr. Faisal,
yeah.
Mr. Faisal, sorry to interrupt you. Please click on hide in the. There is a small windows here. Please click on hide to disappear these
Pardon?
windows. Please click on hide. Yeah, can you see the small windows? Yeah,
Hide, yeah.
yeah.
Sorry.
Okay, that's fine. Yeah.
So this is the components of the hardware. We use it like in my project. There is like 6 components: MAX 30100 and the MQ135, and also MBU 6050, and all the display and node MCU, and also the H11. That's the components. That's the circuit design. We use it like in our project for all the components. You can see the circuit diagram. Can see the MQ135 and the H11 and also MAX 30, and also all AD, the screen, and also MBU. That's the result and discussion. Heart rate and SpO2. Attach the hardware to all AD shows the result. We can see here the heart rate is 91. If you and the SpO2 is 92, 98. Now we control it like as under 95. It comes like alert or message to the doctor. The temperature, it means the temperature of the room, not like the temperature of the patient. We use like 32. We use like the temperature is like 35. Like after like 34, 35, it comes like alarm to the doctor for the temperature of the room, and also the humidity is 83, which is good. When it comes like after 100, it comes like alarm to the doctor. Sorry.
Yes.
We can see here the air quality. The air quality is 238. When it comes like after 500, there is like alarm comes to the doctor, and also failure detection. Attached, we use there is like small component. It's called NBU 6050. That's for the fail detection, and for the air quality we use MQ135 sensor. That's for the components of the air quality. So sensor has the ability to monitor both linear and additional acceleration along its axis. Within the scope of the study, fail detection may be assisted by utilizing the capability. Result and discussion also for the humidity and for the temperature. We can see here 32, which is like it's good because we control it as 35, and also the humidity is 83. We control it as like after 100, it comes like alarm. This project is working perfectly according to the objectives, and also the heart rate sensor MAX 3011. That's the component we use for the heart rate. It's getting the data of pulse rate on the display and send the data to the IoT application. We use like a Blink application. The blood oxygen level also shown on the display, and data is also can be seen over the Blink platform and web page as well. The gel sensor also gets the reading for fail detection and send notification in the form of an LED on the web page, as well as the app. The response for the set temperature and heart rate is quite good, as when the threshold for these parameters reach the maximum limit, the alert can be seen on the IoT application blank. That's the conclusion. An IoT-based patient. So as we know, like nowadays, we use like IoT things for the health care, for the software, for everything. So the IoT-based patient healthcare surveillance device was created as part of this development. The technology utilized sensors to measure vital signs such as pulse rate and the blood oxygen level and the air quality, and also room humidity and temperature of the room. Readings were shown on all CD as well. We can see everything in the LCD. After that, the file is derived from these sensors are wirelessly transmitted to the medical server known as a blank application. Following that, these data are transmitted to the personal smartphone that has been certified and is equipped with the Internet of Things platform. The doctor will then use the result that were obtained of patients and evaluate their current state of health. That's the reference of my project. Thank you for listening. Thanks so much.
Thank you so much, Mr. Faisal. It was very interesting topic. Thank you. Really appreciate. So, is there any question? All right. Who is the next?
Okay, thank you. Thanks so much.
Thank you so much, Mr. Faisal. Who is the next, please?
I am ready, Prof.
Okay, thank you so much, Mr. Ahmad. Please share your screen.
Excuse me,
Yes, we have your
Dr.
screen.
Musa, I have a question, please.
Yes, yes, yes.
I have submit my presentation and also my assignment on the Blackboard, like on
Yeah.
assignment file. That's
Yes,
okay?
yes, exactly. Yeah.
Both of them, the presentation and also the assignment.
Yes, exactly. And if you did some simulation, everything, you can upload the rest of the
All the
document.
codes, everything inside of the assignment.
Okay, it's okay. Yeah. Whatever you
Okay,
need,
thank you.
you can upload it, but these two files should be available in the Blackboard. Okay. Just submit
Yeah,
in
like
the
in
yo. Just submit, upload your file in the Blackboard where I already made. Don't send me in private, in WhatsApp group, in email. Please don't do it, because I have so many students and definitely I will forget it and you will lose your mark. Okay? Just submit where I
have
request.
upload
Yes.
have upload like assignment report and also the presentation, the same file
Yes, exactly.
in the Blackboard.
Yeah.
All right, thank you. Thanks so much.
Thank you. So, Mr. Muhammad
محمد الغامدي.
Saleh Jaman Al-Ghamdi. Yes, perfect. Yes, please start, Mr. Muhammad.
Okay.
Yes.
Bismillah ar-Rahman ar-Rahim. My project is about design and layout optimization of low noise ICs on printed circuit boards. I will try to make it related to a reliability-centered probability
Yes.
framework.
Yeah. Mr. Mohammed, could you please just click on the minimize this small windows or just close it? Yes. Yeah. Close
This
it.
one,
No, yeah. Yeah.
now it's okay.
Yeah. Yes.
The presentation almost covers 8 sections, as mentioned here. From introduction and background, we will identify the research problem and objectives.
Yeah.
We will go through literature review, the theoretical framework, what stochastic modeling we will use, and Monte Carlo simulation.
Yeah.
Then we will finalize with the results and conclusion,
Yeah.
inshallah.
Inshallah.
Introduction and background. So this is bunch of numbers just to show us why this topic is important. 40% of IC field failures come from PCB layout decisions, not the chip itself. $2.1 billion is the annual cost for PCB rework globally, and 6.68% are the noise specification violation with unoptimized layout. So the motivation is that ICs are very critical to and sensitive to PCB layout, such as grounding, routing, and decoupling directly to determine the noise floor. IC manufacturer specifies silicon performance, but PCB implementation introduces uncontrolled noise that exceeds design margins. No probabilistic framework exists linking layout decisions to quantifiable reliability outcomes in mixed single PCBs. So the gap we are working with is that existing studies treat IC design and PCB layout as separate domains, not integrated with the reliability models. Noise voltage probability, VN, rarely quantified from layout parameters, and the Power sound effect modeling for PCB fabrication not linked to specific design for manufacturing rule, DFM violation in the design flow. Our core research question is, to what extent do PCB layout optimization choices shift the probability distribution of output noise voltage and manufacturing defect X? So Vn and X, we will work through the presentation with these two variables. The objectives is to analyze how integrated circuits performance degrades with suboptimal PCB layouting, identify and classify noise and coupling mechanisms from PCB infrastructure, apply MCS, Monte Carlo simulation, to model the mean time before failures under 3 layout scenarios, and provide probabilistic DFM guidelines through the regulatory standards. This is the testable hypothesis for the noise layout link, defect DFM link, and the MTBF recovery. We will go through each one of them in the coming slides, inshallah. The literature review in 2008 or 9 ought established the 3 AMI coupling pathways, which is radiated, conducted, and capacitive inductive. And 2006 quantified signal integrity degradation in mixed single PCBs through transmission line analysis, was mentioned by Paul. Montrose proved that return path discontinuities in ground planes cause 6 to 20 decibel AMI increase, and the rest of them. Most of these references are still the same. They established the main formulas and equations that are used until our current days. They play only now with the design to optimize to optimize and enhance the efficiency of such PCBs. The theoretical framework for our reliability study. This is most of the equation we use throughout the course: the reliability function, failure rate, MTBF, series configuration, parallel configuration, and Weber reliability. And here is the PCB noise and signal integrity equations. We will try to integrate both of them and see the results in the discussion part. The first continuous random variable, which is the output noise, Vn. We have here the mean of 12 microvolt, standard deviation 2 microvolt. and the specification limit is below 15 microvolt. After applying this one, we can see that if the random variable Vn exceeds 15 microvolt, we have 67 failures per 1,000 volts. This is the percentage. Once we go below the specification limit, we enhance this production line to be 2.28%. For the discrete random variable, which is the manufacturing defects X, we have BX0 around 13%, BX less or equal to 1 to 40%, and BX greater than or equal 4 to 14%. And this is the CDF for each of one. So as you can see, they go from 0 to 5, and the CDF gives us the probability between 0 to 1. And if X is equal to 0, we have only 1 in 7 boards is perfect, and this is the percentage. If it's less, which is this one, we have 59% need rework or rejection. And if it exceeds 4, this must be rejected, which is the last 2 rows. Monte Carlo simulation methodology and setup. We used Monte Carlo simulation here to combine the Gaussian, Poisson, and exponential failure times, both 3 of them. We have 3 scenarios, fully optimized with MTBF of almost 50,000 hours, partial protection to 45,000, and no protection to 30,000 hours. We generate 100 samples per scenario in MATLAB, and we will see the results in the upcoming slide. Okay, this is the code and the parameters we set in our implementation. And here are the results. We can see that here the optimized layout, there is no interference at all, 50,000. And here the layout with the protection, and here unprotected or poor layout. We can conclude that the layout optimization recovers 87 to 90% of the baseline MTBF, which is 50,000. Combining grounding and decoupling restored near normal reliability. AMI reduces MTBF by 40% in unprotected analog PCBs. We have the Weibull analysis for the solder joint wear out. The exponential model covers random failures during useful life. We have the parameter set, beta 2.5, 2.2, and 1.8. You can see the greater the beta and the characteristic life of our scenario. We have a better R of T, starting from 98%, 95, and going down decreasingly. And here the wear out phase, the thumb rule, that if beta exceeds 1, PCB solder joint thermal fatigue, copper trace work hardening layout optimization directly extend the characteristic life and slows beta progression. We have a bunch of layout design rules that we can integrate with the reliability. For the grounding strategy, solid copper ground planes, mostly filled above 70% beneath all analog IC sections. Star topology prevents ground loop currents, reduces the voltage, the noise voltage by 20 to 35%. Separate analog ground and digital ground. We can separate both of them only at a single point. Guard rings or copper moats isolate high impedance input nodes, and fire stitching density greater than 4 per centimeter square along ground plane seams. For power decoupling, we can use 100 nanofarad ceramic capacitors per IC power pin, or we can use 10 microfarad bulk cap per rail station that will address the low frequency noise. The capacitor resonance frequency must overlap supply noise spectrum band, avoid phase and trace path between capacitor and IC bin. 2-cap strategy, 100 nanofarad parallel to 100 nanofarad per bin for broadband coverage. For the routing of the PCB itself, we can control the impedance by being matched to 50 ohm or 100 if it's differential. We have a 3W rule that a minimum 3 of the trace width spacing to reduce crosstalk by 70%. For the bins, we can use the 45-degree rule to limit impedance discontinuities. Differential pair length match to equal or less than 0.1 millimeter, critical for SMRR polarization. Route sensitive signals away from switching power traces to be 3 millimeter minimum. For the rules of design to manufacturing, we have a minimum clearance of 0.15 millimeter trace to trace for standard fabrication. Teardrop fillets on all via connections. Solder mask expansion to be 0.05 millimeter per side to prevent any bridging. Via embed avoided in fine pitch SMD less than 0.5 millimeter pitch, and the copper weight optimization to be 1 ounce for signal or 2 ounces for power layers. Results, we can include that the layout is a probabilistic lever, that PCB layout decisions are not binary, right or wrong choices. They shift the probability distribution as we seen previously. The 6.68% specification violation rate is not fixed probability of the IC. It is directly controllable through the sigma reduction via layout optimization. Poisson model for the design for manufacturing as a business KPI. We can track the lambda defects per board, or X, as we mentioned in the slides before, as a revision KPI. Production economics of the Gaussian model. As we mentioned before, that in 1,000 board production run, we have a failure rate of 67 of them that need rework, and we can reduce it if we change the sigma to 1.5, that we have an enhancement to be only 22 boards instead of 67. MTBF recovery through the Monte Carlo simulation. The Monte Carlo simulation results confirm that 40% MTBF degradation from EMI-induced layout failures is not inherent to the IC. The limitation and future work for this study, failure rate estimated from the standards such as MIL 2017F assumptions, not from certified field failure data. The Gaussian model for VN assumes linear, additive, and independent noise sources, nonlinear intermodulation and impulse noise excluded. The Poisson model assumes spatially independent defects, PCB manufacturing clustering effects, not modeled. Single IC analysis, multi-chip system interactions, thermal coupling between adjacent ICs, and board level impedance interactions excluded. Monte Carlo sample size to be 100. We can increase that one to have a better understanding of what's going on through the modulation and simulation of the MCS. Future research, we can validate lambda values using the real inspection data from regulatory standards. We can integrate electromagnetic simulation softwares such as ANSYS or HFSS for parasitic aware noise BDF computation from layout geometry. And we also can extend to mixed Gaussian and Weibull-Boston compound reliability model for full product life cycle coverage. As a conclusion, layout is a probabilistic lever. As we mentioned, PCB layout shifts the probability distribution for both the noise voltage and defects. It's not binary. Can to quantify the noise performance, as we mentioned before, that if sigma decrease, we can enhance the failure rate of the production line. As a design recommendation, priority order for layout to have a solid ground plane high sigma impact, decoupling placement, and we can implement the 3W routing rule for crosstalk and bias stitching for AMI shielding, and finally DFM clearance rules for the yield. MTBF recovery via Monte Carlo simulation. Monte Carlo simulation confirms that 40% MTBF degradation from bore layout, going from 30,000 to 50,000 as a baseline. Implementing 3 targeted layout changes restores up to 90% of MTBF without component level changes. This is the references I used,
Yeah,
and
thank
this is the presentation. Thank you.
Thank you so much. Very interesting topic, and the structure and the quality of your presentation and PowerPoint is very good and similar to Mr. Abdulaziz, so perfect. Can you tell me what was the contribution, main contribution? Is there any main contribution in comparison to other references, or you just implemented this method?
Well, the main contribution is that we use the techniques we studied throughout the course
Mm-hmm.
to try to integrate the design of the PCBs with the production lines,
Mm-hmm.
because as you see through the MCS and the random variables, there is a clear connection that if you enhance the probability of the design itself, you can enhance the production line as well.
Mm-hmm. Okay, very good, very interesting. Thank you so much for your effort, Mr. Muhammad. So, Mr. Ahmad, I think Mr. Ahmad Abu Zinad is ready.
Yes, doctor.
Okay, thank you. Please share your screen. Yeah, hide. Just click on hide. Yes, and yes, share screen. The other, I think the other option. Okay, go to the
What happened to
PowerPoint.
it?
Yeah, yeah. Just
Yes,
in screen mode, please. In the show screen, yes.
like
All
this.
right, yes. Mr. Ahmad Hatem Abu
You know,
Zinad.
yeah.
Okay,
Yes. Yes.
2401792. Yes, please move on. Yes.
Alaikum. Yeah. Yes. Yeah. Yeah. Actually, my project is about a practical project that I applied in my institution, and it is about the design implementation of a modified coding system for MRI scanner to enhance image quality. I will start with the literature review key findings about what it suggests for MRI coding system reliability and image quality improvement. First is the thermal stability affects image quality. MRI performance depends on stable field humidity. High shield temperature can create chiming problems like fast saturation and gradient echo artifacts. Cooling water quality in reliability factor is a reliability factor. Contaminated primary water can cause blockages like dust and dirt on the water pipes. Pressure problems, frequent maintenance, and downtime in the MRI cooling loop. Then the heat exchanger separation is a practical solution. This which applied in our institution now in all MRI systems. Clean secondary loop isolates the MRI equipment from the dirty hospital water, improving temperature regulation and reducing filter-related service burden. The fourth is probability models support reliability decisions. normal, Poisson, and Monte Carlo methods helps quantify uncertainty, failure, likelihood, and probability of good image condition. The key insight, the literature and project evidence support reliability strategy that combines thermal control, cleaner water loop, monitoring, and probabilistic prediction. Introduction and background. MRI image quality depends strongly on thermal stability and magnetic field homogeneity. Poor cooling water quality can increase shield temperature, increase the shield temperature, and cause image artifacts. This is the project source, which is my, I have published a paper regarding this in the International Journal of Current Research, Volume 8 at December 2016. The report reported a normal shield temperature range of 40 to 60 Kelvin. When shield temperature approaches close to or exceeds 100 Kelvin, shimming problems and artifacts may appear. This was the modified heat exchanger-based cooling system was designed and implemented at our institution, King University Hospital, for on 1.5T and 3T Tesla MRI scanners. And this block diagram just in quick, it shows the hospital water inlet and hospital outlet of the water supply, and the heat exchanger system shows the primary side, which is the water incoming water supply, and the secondary side, which is the closed loop system that goes into the machine and comes out of the machine. And the purpose just was to separate the dirty water from the clean water and to exchange the temperature without making the both loops. And it has normal, electronic parts like a water pump and electronic three-way valve and temperature sensors and etc. Research gap. The practical article, as I said, it's published already with the help of some doctors from the hospitals and surgeons and radiologists. Demonstrates success, but a compact, reliability-oriented random variables analysis was still needed. Objective apply on continuous and on discrete random variables to the MRI cooling projects and quantify performance before and after modification. Hypothesis, the modified heat exchanger system improves thermal stability, reduces failure, increases the probability of good imaging and cost-effective. Continuous variable, MRI magnetic shield temperature, T, which is in Kelvin, and discrete variable, number of weekly failure alarms, X. Use analytical probability and Monte Carlo simulation to compare before and after modification. Support findings using practical evidence and MATLAB plots. The temperature model, where T is the MRI magnetic shield temperature and N means the normal distribution. And the equation mean MRI shield temperature usually stays around 50 Kelvin with a small variation around it. The 5 on the power of 2 means the variance, and standard deviation is 5K. And also Z is the just converted temperature value. It tells us how far the temperature is from the average. And for example, if Z was like for a temperature range was between 40 and 60, where the 40K is 2 standard deviation below the average, and in 60 Kelvin is 2 standard deviation above the average. And also this the P is the probability of the temperature, which is in short equals to around approximately 95%. Analytical results before modification, where X is 0, probability of good imaging was 0.2, which is around 22%. And after modification, were around 77% good imaging. Let me explain it more. Peak good imaging between 40 to 60 Kelvin normal range, where X is 0. Let me explain it. Just to give a summary of the equation, where T is the MRI shield temperature, and N normal bell-shaped distribution, and Z converted temperature value used for probability calculation, and number of failures per week is X, and then the average weekly failure. Poisson formula calculates the chances of failures, and good imaging probability temperature is safe and no failure happens. The project improved good imaging probability from 21% before, and modification is to approach 74 after modification. Here I can explain also all the equations that have been applied, as I mentioned, about the temperature stays, the normal temperature usually stays around 50. And by applying the standard deviation is 5, and the 5 to the power of 2 is mean the variance. If we apply the standardization equation, we can calculate the temperature probability by 95% approx in this range, which is the normal operation. Poisson distribution of weekly failure, where X is 0, and we assume that lambda is approx 0 failure rate. We can have a better and more post-modification failure rate is 0.25, let us say weekly, approx 0. It will give us a better good imaging improved, around 77%. And B, good imaging, probability of good imaging between the 40 and 60 Kelvin. Before it will be 0.21, and after it will be 0.74 probability increase, by plus 53 percentage points. Before modification, I assume that we have around 2 failure rate. And the good imaging percentage was around 22, and after modification 0.25, the good imaging were around 74%, the probability of having good image. Project source, a practical MRI cooling article and block diagram. Variable selection, T is the shield temperature, and X is the weekly failure. Probability models, normal plus Poisson before and after, and MATLAB simulation, analytical, and Monte Carlo plots and comparisons. Results interpretation, thermal stability, reliability, image quality. Of course, I used MATLAB, was used to stimulate both analytical probability and Monte Carlo reliability results. Before and VS after comparison, I will show in graphs. Reflected the practical improved achieved by the modified cooling system. Assessment method, how the MRI cooling system project was assessed using practical evidence and reliability modeling. Assessment method, field-based assessment. How it was applied in the MRI cooling project, the modified cooling system was implemented in a real hospital MRI environment. Reliability value shows practical system behavior under actual operation conditions. Assessment method, before and after comparison, cooling response and weekly failure probability were compared before and after heat exchanger modification. Demonstrates the measurable improvement after the design upgrade. And another assessment method, parametric probability modeling. Normal distribution was used for shield temperature. Poisson distribution was used for weekly failures. The reliability value links random variable to the thermal stability and failure occurrence. And another assessment method, which is the Monte Carlo simulation. 100,000 simulation trials were used to validate analytical probability estimates. Reliability value confirms that analytical and stimulated results agrees with practical results and the probability modeling. Sensitivity analysis, failure rate, which is lambda, was varied to study its effect on good image probability, as I showed in the slide before. Shows why reducing failure is essential for reliable imaging. Here is the continuous variable shield temperature. You see here the normal distribution function of MRI shield temperature, which is on the normal range, the PDF with the blue line between 40 to 60 Kelvin. Before modification, as I said, is around 2 failure per week, and after modification is almost 0 failure per week. We have performance metric of P good imaging between the two, the normal temperature. And we can see that we have at high probability of having good imaging in the temperature, in the required temperature range. Comparative cooling response before and after modification. Also here we can see the shield temperature and the time. Before modification, the shield temperature remained above the 60K upper limit, and as it shows here in the blue line. And after modification, the temperature dropped rapidly and stabilized near 52 Kelvin. The modified system brings the MRI into the desired temperature range, operating band. Improved thermal stabilization supports better field homogeneity and image quality. And here we can see the Poisson distribution of weekly failure. Before modification, higher probability of 1 to 2 failure per week, which is around 22%. And after modification, highest probability occur at 0 failure. We can see here the red line, which shows a high probability of having zero failure after modification. Interpretation, the modified system clearly shifts the failure distribution towards fewer weekly failure, consistent with improved maintenance and operational reliability. And we can see here before modification that we might have also more than 2 failures per week, and we have less probability of having 0 failures before the modification. The Monte Carlo output, we can see here some also images which I achieved through MATLAB. I will include the codes in the report, inshallah. The Monte Carlo samples of shield temperature between 40 to 60 Kelvin, and also the samples of weekly failure before modification. We can see here the mean weekly failure is 0.249. Estimated B good imaging is 74%. We can see here the high before modification. We have a high probability of having more failures on the system during the week. And after the modification, we can see here we are having a high probability of having 0 failure after modification. The Monte Carlo results closely match the analytical value, confirming the correctness of the simulation model, which is close to the actual practical values. And also before and after reliability summary, we can see here also the probability of good imaging before and after modification. We are having a high probability of having 0 failures and better image quality. And we can see here how the system is more reliable and having a high probability of 0 failure after the modification during the entire time. And also we have before modification a less probability of having 0 failures, which might occur system breakdown during frequent system breakdown during the week. And sensitivity of good imaging probability to failure rate. Also here, as Zanda increases as a summary, the probability of good imaging decreases sharply. You can see here when the failure, the average failure rate increases. We will have the probability of good imaging will decrease suddenly, as we can see here in the figure. And reducing failures is essential even when thermal control is strong. The modified system increased the probability of good imaging from 0.212 or 0.74. This is an absolute improvement of around 53 plus percentage points overall the rate. And this was the last figures, yeah. And comparative results table. We can see here the summary, the temperature range, the practical temperature range, and mathematical shows before modification and after modification. Thermal model unchanged, of course, because being between in the temperature range, the image and the system will be stable. And the probability of having
excuse me, Mr. Ahmed, to interrupt you. Please, I will send a new link. Please come to the new link, okay? Just to continue, because session will be automatically closed, okay? Mr. Ahmed, are you?
yes.
Yeah. Please go to the, everybody come to the this session, new session. This is the last time. Thank you. Yes, Mr. Ahmed.
Okay, Doctor.
Yes. Just close this one, yes. And click on hide, so yeah.
Yeah, probability of having zero failure, which is before modification, and after modification, failure-free operation improved. And probability of having good imaging also improved. And the Monte Carlo probability of good imaging is also close agreement with analytical results. Note the modified system significantly improved both operational reliability and the probability of good image condition. Here just a picture of what expected outcome of the project. Stable shield temperature between 40 to 60 Kelvin, optimal operating range. Improved image quality, better fat saturation and greater echo image quality with reduced artifacts, and reduced failure and downtime of the system, and also lower maintenance burden, which is cost effective. Why is cost effective? Because before implementing the system, it was we were just changing a lot of filters, and also using a lot of time and breakdown of the system and delaying of diagnostic for the patient, and the MRI cases, and frequently 2 to 4 times we have to change and We have high shield temperature and etc. And this all were affecting patient workflow. But after implementing the system, the machine becomes stable, and rarely we have a breakdown because of high temperature or something like that. Current limitation, the MATLAB model is calibrated from project-aligned assumptions rather than a full historical failure statistics. Cooling response curves are illustrative but consistent with the practical project behavior. Future work use actual maintenance logs to estimate lambda more precisely, fed temperature statistics from measured data, and extended the study to a more detailed like LabVIEW or MATLAB digital models. Incorporate real shield temperature time series data from the MRI system. Use the actual work order, like in our maintenance system. We use actual work order, maintenance history, for more accurate failure rate estimation. Extend Monte Carlo prediction with more uncertainty sources such as flow rate and blockage risk. Develop a broader predictive maintenance and condition monitoring models. Key conclusion and implications. The modified heat exchangers cooling system successfully improved MRI thermal stability and reliability. Shield temperature control was maintained within the desired 40 to 60 Kelvin operating range with high probability. Failure-free weekly operation is increased from 22% before modification and 77% after modification. The probability of good imaging condition increased from 21 to 74 percentage. The MATLAB analytical and Monte Carlo results strongly support the practical project success. These are the references. My article reference, me, Abu Zinada, the corresponding author. If you know him, doctor, he was the chairman of Department of Electrical Engineering before. During that time, at 2016, Dr. Abdullah Dubai, and Dr. Khalid. Yeah. And Dr. Khalid, he helped me a lot of writing the master thesis also. Dr. Khalid Khashoggi and Dr. Muhammad Wazan are radiologists here in the hospital, and they are consultant in that specialty. And also Dr. Jamjoom is a surgeon. So they gave me all the help of having the image and do the ethical approval and etc. and stuff of image patient images on 2016, and also your lectures for the theoretical and simulation Monte Carlo simulation for reliability. I can show you just thank you. I can show you just in quick. This was the article were published, but it was just the practical what I did in the hospital. It was didn't talk about the Monte Carlo and this stuff.
Very interesting, Sam. Really appreciate for your PowerPoint, and again, the quality of your PowerPoint also is very high. The quality of figures, the slides, very professional, and very interesting topic as well. So, very good, yeah. Thanks a lot for your effort, and also please upload your paper also in the Blackboard, whatever you want, But your PowerPoint and assignment report should be definitely uploaded in the Blackboard, okay? So, is there any question? All right, thank you so much for your